Okay, good morning, ladies. Hope you are doing fine this morning. We will continue with speed of reaction. So the first section on speed of reaction is actually looking at how we can um, measure or track speed of reaction as reaction proceeds. And the first method is by measuring the mass of the system so that we can find out the mass loss in regular time interval. Okay, so for example, this was the experiment you saw in the lab where we have acid reacting with a metal carbonate to produce carbon dioxide gas. Carbon dioxide gas then escapes to the environment, so resulting in a mass loss. So what you will see, remember, is the graph that we have seen in class as well. Okay, so when we plot the graph of mass of reaction mixture versus time, we will see that the graph has a decreasing gradient as reaction proceeds. So it's important for you to know how to explain the shape of the graph. So you will see and divide the graph into three sections. The first section is the first part here, where the reaction has just started. So when reaction just started, you will have the most amount of reactant particles. Hence, you will have higher success rate of what we call effective coalition, which we will learn and discuss later. So this effective coalition actually leads to reaction taking place. So the more reactant particles you have, the higher the frequency of effective coalition. Hence, you have a very fast reaction taking place, and you will see that gradient is the steepest. The second section of the graph, okay, you'll see that the gradient is decreasing. This means that speed of reaction is decreasing as well. Reason because as reaction proceeds, some of your reactant particles have formed products, means you will have less reactant particles present and available for more reaction to take place. Okay, and the last section is finally here, where you will see that your graph becomes a horizontal line. So this is when gradient is equal to 0, and it represents and shows that reaction has stopped. So reaction will stop when one or more of the reactants is being used up, is or are being used up. So we have learned under mole concept that the reactant that is used up is called the limiting reagent. Okay, so this is when your limiting reagent is used up. So reaction completes or reaction stops. So you realize that the speed of reaction is represented and measured by the gradient of the graph. Okay, and we can actually do calculation to find out the speed of reaction at specific point in time. So speed of reaction decreases as reaction proceeds, as reactants are being used up. And we know that reaction is completed when the graph has a horizontal, is horizontal or has a zero gradient. Okay, this means that the mass of the system remains constant, and hence the mass loss is 0. Okay, do take note that your graph will not reach 0 and touches the x-axis, because while gas is escaping, you still have the other contents like your excess reagent and the other products that are being formed, and they will not escape. Okay, so if your reaction is taking place at a faster rate, okay, so if you have a second reaction taking place at a faster rate, you will realize that the gradient of the graph should become steeper, because remember gradient represents speed. So the faster reaction means you have steeper gradient. So your graph will look something like this. So a steeper one, and it should still go back, or rather it should still end up with the same height, because they didn't mention about changing the amount of limiting reagent. So this is when you have a faster reaction but still the same amount of limiting reagent. Hence you have a steeper graph at the start and the middle of the reaction, and the reaction completes earlier, but the final height remains the same. Okay, so for speed of reaction experiment, you have to mix the reactant and start the stopwatch at the same time at the start of the reaction. So this requires coordination. So the key experimental error is that we may either delay in starting the stopwatch, hence resulting in the time taken for reaction uh, or time taken to be shorter than expected, or the mass loss will be larger than actual. Okay. On the other hand, you may, because of the coordination needed, start the stopwatch earlier. So if you have started the stopwatch earlier, then what happens is the mass loss may become smaller than actual. Okay, so please remember the experimental error because this is important. Okay, so we have gone through this in class, so this is a quick recap. Now we go to the second way to measure speed of reaction, which is especially useful if one, you have gas being produced and you can collect the gas and measure the volume of gas produced, or two, if you have a precipitate or colored product that is formed, okay, then you can measure the time taken for the precipitate or the colored product to be formed. So we'll focus on the first example first, which is when in a reaction, gas is being produced. So we can track the speed of reaction by measuring the time taken for a fixed volume of gas collected or the volume of gas collected in a fixed period of time. So this is for reactions that produces a gas. So for this reaction between metals and acid, you will see that you form salt and hydrogen gas. So hydrogen gas can be collected and you can measure the volume of the gas produced. For this reaction, we usually don't use the first method, which is mass loss, because hydrogen gas produced generally is lighter. So you may not have a significant loss in mass if you're tracking the mass of the reaction system. So how do you do the experiment? Remember in class we have done a demonstration. So basically you set up the reaction vessel and set up the reaction as seen. Okay, then when you start the reaction, the gas will be produced and be collected in the gas stream here, right? The gas stream usually is graduated, means they are marking for you to then record the volume of hydrogen gas produced in fixed time intervals. So it can be every 30 seconds, it can be every minute. Okay, and this works if really the one of the product is a gas. Okay, so first question here, you see that they ask you to clean the piece of magnesium with sandpaper. So why do you think you need to clean the magnesium with sandpaper? Okay, remember magnesium is a reactive metal. So being a reactive metal, it can react with air that's around it. What do you think will be formed? Okay, so I hope you have gotten it, that indeed magnesium, because it's a reactive metal, it can react with oxygen that's in air to form magnesium oxide coating. So this layer of magnesium oxide will actually prevent the metal from reacting with the acid when you sort of start the reaction. So at the start of the reaction, you will not see any effervescence because you actually need to wait for the layer of magnesium oxide to react with acid to form salt and water first. Only when this layer of magnesium oxide is being removed or being reacted, then you will start to see reaction taking place. Okay, so instead of just waiting for reaction, you can actually do the sandpaper, use the sandpaper to clean off the layer of magnesium oxide first. Okay, so after doing the reaction and measuring volume of hydrogen gas produced in fixed time interval, you can also plot a graph, and your graph will look like this. So this is the graph of volume of hydrogen versus time as reaction proceeds. You will realize that it follows a trend, and hence the explanation will be similar to the one when we use tracking of mass loss over a period of time, okay, as reaction proceeds. So again, you can divide the graph into three parts. So first part you will see is at the start of the reaction. So again, at the start of reaction, we have the most amount of reactant particles, hence the frequency of effective collision will be the highest. So you will have the fastest reaction rate here, hence the gradient is the steepest. Then you have the second part of the graph here. Okay, this is when some of the reactant particles have already formed products. So you will have less reactant particles present. So the frequency of effective collision will drop, reaction rate will slow down, and the gradient will become less steep. Finally, is your last part of your graph where your gradient will become zero. This is where reaction has stopped. Again, likely because your limiting reagent, one of the reactant, is used up. Okay, so gradient decreases as reaction proceeds, which is the same trend as if you use method 1 to measure speed of reaction. Okay, so for speed of reaction, you do can plot the graph of volume of gas versus time, and the speed is measured by the gradient of the graph. And we can see that the gradient becomes gentler, which shows that speed of reaction decreases as reaction proceeds because reactants are being used up. And you know that reaction completes when the volume of gas remains constant. Okay, this is because reaction has completed, so you do have the maximum amount of gas that's possible to be produced. Okay, similarly, you can also predict how does the graph or how does the curve looks like when you have a faster reaction. Let me give you a bit of time. You can do a sketch on your own notes first. How do you think the graph will look like if you have a faster reaction? Okay, I hope you've gotten it. A faster reaction means you have a steeper gradient, or your curve should look like this. Right? The faster reaction means you have a steeper gradient. Okay, but again, the height of the graph, okay, if let's say you have the same amount of limiting reagent, the height of the graph should be the same as the original graph, unless the question tells you that the amount of limiting reagent is changed. Okay, is there another way to determine the speed of reaction by measuring the volume of gas produced with time? Now, because you have two factors here, one is the volume of gas and one is time. So you can either fix time. Okay, so like in this case, you fix time and you measure volume of gas in fixed time interval, or vice versa, you can actually fix the volume. Okay, then you record the time taken for a fixed volume of gas to be produced. So two variables, you fix one and you measure the other one. Okay. Now in doing speed of reaction experiment, remember you are using the stopwatch and you're starting the reaction at the same time. So there will really be this experimental error where either you delay in starting the stopwatch or you start the stopwatch earlier. So that will have an impact on the results. But please again don't just say resulting in inaccuracy or resulting in inaccurate results. You have to say what is the inaccuracy. So in this case, you're measuring volume of gas. So if there's a delay in the start time, what happens is the volume of gas collected is larger because your reaction is started before you start timing. Okay, or if you have started, if there's a delay in your starting of your stopwatch, then what happens is the reaction has started before you start timing. On the other hand, if you have started the stopwatch earlier, what happens is timing started first before reaction starts. So the volume of gas is actually smaller than natural. Okay, so take note, you do have to explain how the results is being affected. Okay, and finally, the third method to measure speed of reaction is by measuring the amount of product produced with time, especially if your product is a precipitate or colored product. Okay, so one example is actually like the iodine clock experiment that we have done in class. So when you mix two colorless solution, what happens is when reaction takes place and the iodine produced reacts with the starch, it gives a blue coloration. You can take the time taken for the blue coloration to appear. Okay, another example is shown here where you have a reaction of sodium thiosulfate with dilute hydrochloric acid. So what you will see here is you have a solid that is being formed. So by looking out for the solid, you can actually measure the time taken for this solid to form. So what we do is we do a setup like this, where you have your reaction solution, the sodium thiosulfate solution inside a conical flask. And to help you have a better observation, you can actually put it on a piece of paper with a cross marked on it. So the moment you add in the acid to the sodium thiosulfate solution, you start the stopwatch. What happens is the reaction will take place, okay, and you form a solid. So the point when the cross becomes obscured because of the solid being formed, you can stop timing, okay, and you can repeat the experiment, okay, maybe at different conditions. So let's say you're investigating how temperature can affect the speed of reaction. So you can repeat the experiment, but at different temperatures of your sodium thiosulfate solution. Okay, so like I said, this is for reaction where you have a precipitate or a colored product that is being formed. Okay. So if you are investigating, say, the effect of temperature on speed of reaction, what you realize is that at higher temperature, the time taken for the cross to disappear or the cross to be obscured by the sulfur that is being formed, the time taken will be shorter. Because the higher the temperature, the faster the reaction rate. So temperature is really a key factor that will speed up reaction. So the higher the temperature, the shorter the time taken for the cross to disappear from view, and the higher the temperature, hence we can conclude the higher the speed of reaction. We can also plot a graph of 1 over time against temperature, because remember speed is actually the amount of product formed per unit time. So you have time being the denominator here. So if you plot this graph, you realize that this graph shows an upward trend, which shows that speed of reaction will increase as temperature increase. Okay, so with that, okay, maybe you can take a look at page 7 of your notes. Okay, there are some quick check question there. Okay, give yourself some time to go through the quick check question before you look at the next video for the answer.